Hello chemistry students, this is Dr. Tullis and we are looking at chapter 15 here, looking at the principles of chemical reactivity, equilibria. There are 6 sections that we will be covering in this chapter. In the first section we will look at understanding that chemical reactions are reversible and that chemical equilibria are dynamic. All chemical reactions are reversible, at least in principle. The concept of equilibrium is fundamental to chemistry. Think of a chemical reaction where I have 2 reactants, A plus B, and they create products C and D. This is a forward reaction. What if I went in reverse? So I flipped this around. So my reactants now are C and D reacting to form A and B. So this is the reverse reaction. Now initially when I started this reaction, right here, initially I only had A and B. So only that forward reaction is possible. Think about it. When I have 2 reactants and I have a certain amount of both of those reactants, there is no product formed at that point yet. So it can only move in the forward direction. But once I have A and B starting to react and form products, so as those products build up, the reverse reaction then speeds up while the forward reaction slows down, and eventually those rates are equal. There's a lot going on in this page, but I want you to look at letter A here first. Imagine what will happen if the solution of calcium plus 2 ions and HCO 3 minus ions are in a closed container, unlike the reaction in this figure. This is an open container, but think of if it was in a closed container. So here are my reactants. As the reaction begins, we have our calcium and HCO reacting to give products at a certain rate. As the reactants are depleted, the rate of this reaction slows down. But if this was a closed container, at the same time, the products, which are the calcium carbonate, the CO2, and the H2O, these products then combine to reform the calcium ions and the HCO ions. Eventually, the rate of that forward reaction, which is the formation of the calcium carbonate, and the rate of the reverse reaction, which redissolves that calcium carbonate, become equal. Both the forward and the reverse reactions continue to occur, but no further macroscopic change is observed. Equilibrium has been achieved. So here is my forward reaction. Here is the reverse reaction. So all I did was take my products here and I made them the reactants to make new products, which are the reactants from the original. This concept of equilibrium is super fundamental in chemistry. It was introduced back in chapter 3, which was Gen Chem 1. So you've already encountered its importance, and you've seen that when we've looked at solubility, acid and bases, and changes of state. But we are now emphasizing the following. We already said this back on slide 1. Chemical reactions are reversible, at least in theory. Number 2, chemical reactions proceed spontaneously in the direction that leads towards equilibrium. Number 3, in a closed system, a state of equilibrium between reactants and products is achieved eventually and remains unless there is an outside disturbance. And number 4, outside forces can disturb the equilibrium. Now, a major goal of our future exploration of chemical equilibria in this and the next 2 chapters will be to describe chemical equilibria in quantitative terms. When we are writing a chemical equation that is at equilibrium, we use a double arrow symbol, which indicates that the reaction is reversible and is a signal to you that the reaction will be studied using the concepts of chemical equilibrium. So if I think about that past example where I wrote 2 equations where these were the reactants in one and these were the reactants in the other, we can simply show with a double arrow. When I write a reaction that's at equilibrium with the double arrow, I'm saying that the forward rate is equal to the reverse rate. I can simplify that, and this is saying the same thing. The forward rate is equal to the reverse rate. We know from the last chapter that we write rate is equal to K times the concentration of A in this case. So I could say that the rate, which is the forward reaction rate times the concentration of A, is equal to, now going in reverse, if this was a reactant, I would say that rate is equal to K going in reverse times the concentration of B. If I set these two equal to each other, so if I said rate and rate, I can say that Ka is equal to Kb. This is my forward, this is my reverse. So the rates are equal. This is three ways of saying that the forward rate is equal to the reverse rate. That does not mean that the concentrations are equal. No. Rates, remember, are determined by concentrations and activation energies. The net concentrations do not change at equilibrium. Those rate constants are also not equal. Section 2, we are focusing on the equilibrium constant expression, K. When I write that general equation, A plus B equals C plus D, and the little letters are the coefficients, I write at equilibrium the equilibrium constant. I write as products over reactants, and this is the concentration of products over reactants. So in this case, these are my products, so I'm going to say the concentration of C times the concentration of D, and those coefficients that are in front of C and D are my exponents. Those are the products over concentration of A times the concentration of B, and if there are any coefficients in front of them, then those are the exponents there. Let's look at this example. We're going to look at this a few times in this lecture. If I said hydrogen gas plus iodine gas to give me 2 moles of HI gas, I would write my K constant expression at equilibrium. I would say the concentration of HI squared, again this is concentration, and these are my products, over, these are my reactants. I would say the concentration of H2. Notice there's only 1 mole of H2, and so I don't need to write a 1 right there. It's just implied. Times the concentration of I2. Again, there's a 1. I can just leave it as is. And this is going to be equal to my K constant. When I solve this, assuming I know the concentrations of my reactants and products, if my K is greater than 1, then the reaction is said to be product favored. Products are on the right, so my reaction is going to be pushing to the right to create those products. If my K is less than 1, then the reaction is said to be reactant favored. That means my reaction is going to be pushing to the left to create more reactants. Why don't you try writing the equilibrium constant expression for this reaction? Pause the video. I would write, notice that there's a lowercase c here. Lowercase c means concentration, as opposed to I could find the equilibrium constant expression for pressure. But here we're focusing on concentration. Concentration with our brackets. Oftentimes you'll just see this left off and it's just K. But notice that my products, so I would look at the concentration of NO2. There's a 2 in front of it, so it's squared. That's my products. Divided by my reactants here, so I'd say the concentration of N2O4. There's no coefficient, so there's no exponent. Let's look at some rules for writing our equilibrium constant expressions. We include gases and solutions. We do not include solids, pure liquids, and water. Because solids and liquids never appear in equilibrium expressions, if I have an equation like this and I said to write my K expression, products over reactants, so I would say the concentration of my product, which is SO2, divided by my reactants. Notice this is a solid. We just don't include it. But that is a gas, so we would say the concentration of O2. So my K expression leaves out the solid, the pure liquids, and the waters. K has no units. Remember again, each concentration is raised to its stoichiometric coefficient. All concentrations are equilibrium values. Products appear in the numerator, reactants are in the denominator. Products over reactants. The value of K depends on the particular reaction and the temperature that it's at. Concentrations are in molarity, capital M, which is moles per liter. Concentrations can be in aqueous solutions or in gases. So we can look at concentrations of aqueous solutions or concentrations in gases. We can also look at gas systems using Kp, which is looking at partial pressures. So if you see units like ATMs or millimeters of mercury, we're looking at gas pressures. And we would use the same setup. We would look at products over reactants. So in this case, I have H2 plus I2 to give me 2HI, the same expression. But if I was given units of, instead of capital M, molarity, if I was told that I had 1.2 ATMs of hydrogen gas, 0.9 ATMs of iodine gas, and 1.78 ATMs of product, I would simply, instead of doing brackets, I would say the pressure of HI squared divided by the pressure of hydrogen times the pressure of iodine. And neither of those have exponents because there's no stoichiometric coefficients in front of it. Why don't we include solids? Well, because experiments showed that equilibrium concentrations of other reactants and products don't depend on how much solid is present. The concentrations of solids are essentially constant. Why don't we include water? Well, let's say in this equation I've got hydrochloric acid plus oxygen to give me water and chlorine gas. Water's concentration is very high in a dilute HCl solution. So the concentration of water is essentially unchanged. Here would be an example if I had a mixture of hydrogen and nitrogen gas in a vessel. So hydrogen plus nitrogen gas, these are both gases, and they're allowed to get to equilibrium. The equilibrium mixture of gases was analyzed and found to contain 7.38 atmospheres of hydrogen, 2.46 atmospheres of nitrogen, and 0.166 atmospheres of ammonia, NH3. This is the equilibrium, so I have a double arrow. Calculate the Kp, products over reactants. Let's make sure that I'm balanced. I have 2 H's on the left and 3 H's on the right, so I'm not balanced. I'm going to put a 3 over here and a 2 over there, so I have 6 H's on both sides. That gives me 2 N's and 2 N's. Great. Now that I have a balanced equation, I can write my Kp. I'm looking at pressure, so I would say the pressure of my products, NH3 to the second power, over reactants. Pressure of H2, that would be to the third power, times the pressure of N2, and that's just raised to the 1. Let's set it up. My pressure of NH3 squared, so 0.166, this is all in atmospheres, over my pressure of hydrogen, 7.38, that's cubed, times N2.46. Now this number is less than 1, 0.0000279. Let's go back to look at what that means. So that K value was less than 1, which means it's reactant favored. So this means that we have more reactants than products at equilibrium. So the reaction will shift to the left or favor the reactants. Why don't you pause here and write the equilibrium constant expressions for the following reactions, and these are all in concentrations. So we're looking at K for the concentrations of A and B. Let's see how you did. My product here, NH3 to the second power, over N2 times H2 to the third power, the same as what we had before, except for that was looking at partial pressures, and this is concentration. Here I have HCO3 minus H3O plus, both of those raised to the first power, all over H2CO3, and we exclude water. Why don't you try these three? My product, I would have the concentration of CO to the second power over the concentration of CO2 to the first power. We don't include solid carbon. The second one would have the concentration of copper plus 2 ions times the concentration of NH3 to the fourth power, all divided by the concentration of Cu NH3 fourth. And the last one, I would have my products all raised to the 1 divided by CH3 CO2 H, not including water. That would not be in the denominator. Now we looked at that small value of K, but a large value of K means that the concentration of products are much greater than that of the reactants at equilibrium. That would mean that we have a strongly product-favored reaction. A chemist would say that the reaction has gone to completion. So again, if my K is greater than 1, equilibrium lies to the right and its product favored. So a large K means it's going to the right, and to the right are my products, so product favored. If K is less than 1, the equilibrium lies to the left, which means it's reactant favored. Little reactants will have been converted to products. And if it's about 1, then we need to do the calculations because it may not be immediately clear. Let's look back at that reaction, the Haber reaction, N2 plus 3H2s to give me 2 NH3s. If, when I calculate whatever concentrations were there, and I got a very large value here, that means I have a product-favored reaction, and the concentrations of my products were much greater. It's kind of like looking at a fraction. If I had a value of 2/4 versus a value of 4/2. 2/4 is the same as 1/2, which is 0.5. But if I have a larger numerator, so if my numerator went from 2 to 4, so this is my products on top. If I increase the concentration of my products from 2 to 4, decrease the concentration of my reactants, remember the reactants are in the denominator, from 4 to 2, I then have a K value of 4 divided by 2 is 2. So a larger K value means I've increased the concentration of my products and decreased the concentration of the reactants. A K value of 2 versus a K value of 0.5. A larger K value means it's product favored. A smaller K value means it's reactant favored. So hopefully you feel confident writing that K expression. Then we have a reaction quotient, Q. Notice I can write a Q expression and it looks exactly the same as that K expression. Has the exact same form. Now for K, we look at the concentrations at equilibrium. For Q, we can look at concentrations that are at any point of the reaction, not necessarily when it's at equilibrium. If Q and K equal each other, our system's at equilibrium. If Q does not equal K, then we are not at equilibrium. If Q is less than K, some reactants must be converted to products for the reaction to reach equilibrium. This will decrease the reactant concentrations and increase the product concentrations. If Q is greater than K, some products must be converted to reactants for the reaction to get to equilibrium. So that will increase the reactant concentrations and decrease the product concentrations. Let's look at an example here. We're looking at the transformation of butane to isobutane. So here's our reaction. Butane is my reactant, isobutane is my product. Here is my reaction, and I'm told that the K constant at equilibrium, so I'm taking my product, which is the concentration of isobutane, over the reactant, which is the concentration of butane. And I'm told that that K value is 2.58 at 298 Kelvin. But let's say I have a mixture of 0.003 moles per liter, which is capital M, of butane. That's my denominator, so I'm going to put this value in my denominator, and I have this concentration, 0.004 capital M, of isobutane. That's going to be my numerator. So if I have these values, I can find my reaction quotient. So let's do that. My 0.004 divided by 0.003 gives me a value of 1.3. How does that compare to the K value of 2.5? Well, 1.3 is less than 2.5. So my Q value is less than the K value. That means we are not at equilibrium. How do we make a value larger? Well, I need a greater numerator and a smaller denominator. So my product concentration needs to increase and my reactant concentration needs to decrease. Let's look at this example. We're looking at nitrogen dioxide can exist in equilibrium with N2O4, and we're given our K at equilibrium. First I'm going to write my K expression. Product, so I'm going to write N2O4 over reactants, NO2. NO2 would be squared. So the concentration of N2O4 divided by the concentration of NO2 squared. Suppose that the concentration of NO2 is 0.015. So that's my denominator, 0.015, and I'm going to square it. and the concentration of N2O4 is 0.025. So that's my numerator, 0.025 is Q, and this is our Q. Is it larger than, smaller than, or equal to Kc? Well, let's do the math. When I plug it in, I should get a value of 110. Well, 110 for our Q value is less than 170. So Q is less than K, because 110 is less than 170. Therefore, we are not at equilibrium and would need to increase our Q. And remember, to get a larger Q value, we need a greater numerator. So my products will need to increase in concentration, and the reactants will need to decrease in concentration, which means my NO2 will need to convert more into products. This question has two parts. It wants us to go back to that butane and isobutane equilibrium. So if I take my products, that was the concentration of isobutane over the concentration of butane is equal to K. And we're told that our K at equilibrium is 2.50. Is the system at equilibrium when the concentration of butane is 0.00097? So that's the denominator. And the isobutane is 0.00218. Well, let's see. If I divide those, I get 2.2. How does that relate to 2.5? That means that my Q is less than K. So the concentration of isobutane needs to increase. And in order for the concentration of isobutane to increase, that means my reaction needs to go to the right, so the concentration of butane needs to decrease. Let's look at B. What about when butane's concentration is 0.00075, that's the denominator, remember, because that's the reactants, and the isobutane is 0.00260. If we plug that into the calculator, I get a value of 3.5. Now my Q is greater than K. So now we need to increase the concentration of butane and decrease the concentration of the isobutane in order to get that 3.5 down to 2.5. That will get us back to equilibrium. Let's look at this example. We're told that H2 plus I2 gives me 2HI. We're given a K value of 64. We're told the concentrations of each of these three. See if you can set up your K expression and plug in your values and tell me, is the system at equilibrium? And if not, do we need to shift to the right or shift to the left? Pause the video here. When I did the math, I got Q is 0.01, which is way less than 64. Therefore, we are not at equilibrium, and we need to increase that value of Q to get it to be closer to that K value at equilibrium. In order to increase or get a greater number, we need to shift to the right. We need a greater concentration of my products and a smaller concentration of my react. How about now with these concentration values? Well, if I plugged in these values into the Q equation from before, I would have 8 squared, which is 64, divided by 1 times 1, which is 1, and I would get 64. So Q in this case would be equal to K. So there would be no shift. It's at equilibrium. One last practice one with this equation. Given these concentration values, is the system at equilibrium? And if not, what would need to happen to get it to equilibrium? When I plug in those values, I get 400 for a value of Q, which makes it much greater than the K value of 64. So it's going to need to shift left. We need to increase the concentrations of the reactants and decrease the concentration of the product, meaning the reaction needs to lose the HI, therefore go to the left to create more H2 and I2.